sure that everyone's seen click through the slides. Great. Right, so let's go ahead and get this started. Hi, I'm David. I'm going to talk today about some work that we just put up on archive with both Chris and David Knott. This is really an extension of some earlier work in both the BSL world and the ABC world, where we're kind of trying to figure out how these methods behave when the model is wrong, when the model is misspecified. And again, the setting and the motivation, again, is the motivation that we've seen throughout this entire workshop, which is Bayesian inference in intractable or computationally difficult likelihoods. Now, what I'm going to highlight here is a latent belief, really, that when you pick a model, you believe the observed data is essentially drawn from some member in that model. And what we do in approximate generative methods is we basically use this model class to conduct inference on the unknowns about that model. I'm going to denote them throughout as theta in some set theta, cat theta. And I'm going to specifically think about approximate generative methods. And I mean approximate generative methods in the sense that I'm going to talk only about the case where I degrade the data set Y down to summary statistics, which are much lower dimensional. That's why these methods are approximate. I'm going to talk about replacing likelihood evaluation with model simulation. That's why they're generative. Just as a way of setting notation and giving you an idea of how these methods work. Of course, we all know this, but it allows me to set notation for the rest of the talk. So when you work with these type of methods, what you're basically saying is that the observed data we have, Y, is generated from some member in that family, and this guy gives me a sample that I observe. And we can kind of think of that if you give me a value of theta, and this little pi theta here denotes our prior beliefs about theta. You give me a theta that defines a member in the class, I can simulate data according to that. If I then have a summary statistic mapping, I can apply this mapping to both the observed and simulated summaries. And we're going to assume here that those summaries are pretty well behaved in the sense that they converge in a well-defined sense to well-defined limit counterparts. And then all of these approximate generative methods, I don't really care how you're looking at them. They really just try and select values of theta that kind of make a distance small. And what I mean by this is this distance can change. It doesn't necessarily matter in terms of what specific method you're working in. You can kind of recreate them in this world. But this means that you generally only get an approximate posterior that is not conditioned on your data set, but is only conditioned on the summaries. Now, of course, this doesn't deal with the cases where, like Yen talked about yesterday, where you're conditioning effectively on full data distances and stuff like that. Chris is also going to talk a bit about that in the next talk. Now, the two most common approaches when you're dealing with these summaries are, of course, to use ABC, which basically you can kind of think of as selecting a value of theta according to some kernel probability that depends on some tolerance parameter epsilon and some distance d. And Bayesian synthetic likelihood is an alternative to this in a sense that it doesn't necessarily select it this way, but it does work on a well-defined distance that we'll talk about just a little bit. The idea of BSL is a little bit different in that basically what we're going to do is we're going to simulate IID replications of the data, and we're going to calculate for each of those replications summary statistics for each of the m different data sets. I'm then going to take a sample mean and a sample covariance of those summaries. Generally, then I'm going to use MCMC methods to access what we refer to here as the BSL posterior. Now, the difference here is that we're really having to account for this kind of randomness that we're using to simulate the data. So you can think that the actual BSL posterior is not proportional to a normal kernel. It's actually proportional to the expectation of this normal kernel times the prior. Now, a few words before we go into deeper territory. The reasons for using ABC versus BSL, I'm not going to really get into these, just as much to say that essentially ABC kind of acts like non-parametric conditional density estimation, where the bandwidth or tolerance used is epsilon. What this really means is you kind of have this bias variance trade-off that always happens in ABC, where you're kind of trading off potential bias for variance, in the sense that if you choose a larger tolerance, you might actually get more precision in practice. Now, BSL has a different type of trade-off in the sense that BSL effectively assumes, in the simplest case, you have a normal approximation to the likelihood of the summaries, which, for those of you who've done frequentist inference, you can kind of think of as quasi-maximum likelihood in a sense. Now, the tuning parameter in BSL is not an epsilon, it's an m. It's a number of simulated data sets, and people have already talked about this quite a bit, so I'm not going to rehash this. The point here is that if the model is very complex, or potentially if the model is misspecified, and may have to be very, very large in order to get movement in that MCMC chain in order that you can actually sample this posterior here. For this talk, I'm really going to focus on BSL, and when necessary or when important, I'm going to compare the results we're going to get with ABC. So what's the question of this paper? Or why are we interested in studying this? Well, I'm interested in studying this because by the very nature of the models to which BSL is being applied, they're very complex. You can't look at the likelihood they're intractable. And that gets my hackles up because there's this, of course, well-known model complexity caution from Box, which is that since all models are wrong, the scientists cannot obtain a correct one through excessive elaboration. It's a little worrisome because when you specify a model in BSL, what you're kind of saying is that there is a value in the parameter space or that defines that model class for which implicitly the data has been generated, at least as measured by the features of the summaries we're interested in. And we go into more detail on this in the paper, but I'm just going to kind of say you can think about it like this. If the model's not correct, the model itself may not be able to replicate the behavior of the observed summaries, i.e., more specific, there may not exist a value of theta such that the difference between A to Z and A to Y can be minimized or go to zero. Just to show you, okay, so that's our setup. You might be asking now, okay, why does this really matter? What I'm going to show you, hopefully, is that this can really, really matter in practice, and there are potentially severe consequences in BSL for using the specified models. So to do this, I'm going to go back to a little toy example. I'm not going to do the MA2. I'm going to make my life simpler and do the MA1. So our assumption here is that the DGP for the observed data is a moving average model of order 1, and the innovations of that evolution equation here are standard normal. I'm then going to take as my summaries the sample variance and the first order auto covariance. Now this is our assumption. However, the truth is that the observed data, YT, evolves according to a stochastic volatility model. Now, the thing to recognize about the stochastic volatility model is that its first order auto-covariance is 0 in the limit. There is no autocorrelation at the levels. Given that, you would expect, or you would hope, that BSL, ABC, these methods that would use this, would give me back a value of theta with high posterior mass around 0. So what you can show is that the observed summaries, when I use the sample autovariance and the first order autocorrelation, converge in probability under the true model to this guy here, i.e. the first order autocovariance is 0 for all processes in the SV class. And you have this kind of variance form, which works out to kind of just be the variance of a log normal. In contrast, the simulated summaries that you would work at with BSL converge in probability to this functional here. Right, so what this basically means is that if there doesn't exist a value of theta such that this is satisfied, BSL is misspecified in the sense that with probability converging to 1, the simulated data cannot match the observed summaries. One way of saying this is that the observed summaries are not in the support of the simulated summaries for any value of theta with probability converging to 1. So you may think, well, this may not matter a whole lot, and indeed it doesn't matter when the model is very kind of lightly misspecified. So let's take a couple of different scenarios to look at here. I have 6 different values of that first autocovariance, i.e. the sample variance. You can kind of think of this 0.01 value of this guy as representing significant misspecification, tending towards almost no misspecification in the sense that if this guy here is 0.99, then the difference between this for the smallest I can make that gap is 0.01, which is not big, right? So let's go ahead and look at the BSL posterior, and this is going to be the exact BSL posterior. I'm not going to end up doing any sampling here because it turns out that you can actually estimate the mean and variance of those summaries with quite a bit of effort, so you can actually form the exact BSL posterior. And we're going to look at that posterior for 2 different sample sizes: a solid line, which is based on 100 observations, and a dashed line, which is based on 1,000 observations. And so I'm going to show you those 2 different posteriors across 6 different values of kind of quote unquote misspecification. So the top left, or the top left of my screen, is the biggest value of misspecification to the lowest. And what you see here is something I would have never expected to see looking at exact posteriors for an MA1 model parameter. So what you see in the case of very misspecified models is that the BSL posterior is concentrating onto the boundaries of the parameter space. For less misspecified models, it's concentrating on the interior of the parameter space, but it's bimodal. And indeed, what you can show is if I look at any value of this gamma naught between 0.1, say, and up to 0.49, it's bimodal. And eventually what happens is the modes converge and you get this area of posterior flatness. But after about 0.75, you get a single mode that comes about. And so the posterior looks nice, it looks Gaussian. So in a sense here, in my opinion, the consequences for misspecification in BSL, severe. Depending on the level and type of misspecification, you can have multimodality, you can have convergence onto a boundary, you can have posterior flatness. Dogs, cats living together, mass hysteria, to quote Peter Venkman from Ghostbusters. So what I want to do next is I want to kind of explore some of the theoretical behavior of this and why it's happening. Then I'm going to talk a little bit about comparing this behavior in BSL to the behavior in ABC. Then I'm going to show you how, using something that Chris and I have come up with in a paper that's recently coming out in JCGS, you can fix all of this, basically. Right, so why is this happening? Why is misspecification so destructive in a sense in BSL? Again, just to remind you that the assumption is our observed data is generated from some member in that class for some value of theta, but the truth is that there is no value of theta than which I can match the actual DGB. Now, the reason this is happening, this kind of multimodality in a sense, is that unlike ABC, the BSL posterior is really driven by what looks like a Mahalanobis distance, i.e. in ABC, when we use a proper distance, we're measuring absolute magnitudes of differences between simulated summaries and observed. BSL, on the other hand, measures relative distance, which means even if this is very, very big, there might exist a value of theta that's very, very small here, or makes this very, very big. So when I invert it, the overall distance is very, very small, which is exactly why you're seeing those boundary issues pop up and that multimodality in BSL. Stated kind of in words, basically misspecification induces a mismatch between the observed and simulated summaries, and we say that the BSL posterior is misspecified if in the limit there is no value of theta that makes this distance 0. And indeed, you can show that in those examples in the MA1 case, that is exactly what happens. Now, the real kicker here for me is that if I were to do ABC, say in that MA1 example, you can actually show that this limit minimizer of that criterion function exists, it's unique, and it's actually 0. So what you can show is if you were to do ABC in that MA1 example, the ABC posterior is unimodal, and it concentrates onto theta star being 0. The multimodality in the BSL criterion function exists solely because we're using this relative measure of distance, i.e. relative being in terms of these sigma n units, i.e. the sample variance. And what this means is that depending on the level of misspecification, you can get very, very different values of theta star. What you can show here is if I'm doing ABC, for instance, this theta star is unique and it's 0 for all values of B naught. For instance, but in the case of BSL, if I have very high misspecification, you can show that that posterior converges onto a boundary. If it's not as bad, it converges onto a multimodal guy in the interior of the space. And if there's a single mode, which happens actually if B naught is larger than about 0.5, you converge to the same point as ABC, i.e. you collapse onto 0, which again is the value that minimizes the limit difference between the observed and simulated summaries. So what's really happening here? Is the BSL posterior still regular? Well, it's multimodal, but when you go back and look at it, if you squint really hard, you can kind of see that if I was to look just around this mode, just around this mode, just around this mode, or just around this mode, it looks pretty Gaussian actually. So what you can actually show is something that I think is rather interesting. Basically, you can show that the concentration is basically Gaussian, but it's only Gaussian around the modes of the log synthetic likelihood. In particular, if I define a localized version of the parameter, which again is just a local translation of the space, then under some strong assumptions that require pretty strong smoothness of the log synthetic likelihood, there exists a density such that's that's a normal with mean 0 and variance given by the second derivatives of the limit of this criterion function, such that for any finite gamma, if I look only in a gamma ball around this T, that BSL posterior is indistinguishable from that kernel of a normal. And the rate of convergence of that is OP1 on M, because you pay this penalty because you're simulating M data sets in BSL. So if M goes to infinity, this goes to 0, and you get convergence kind of in a local neighborhood to a normal. So really what this means is that in this, if you have this local mode issue in BSL, what's going to happen under some regularity conditions is that it's still going to be Gaussian. The concentration is still going to be regular. It's just going to be regular around the modes, i.e., you still have some regularity. There's kind of just more of it in a sense. This I've only ever seen this behavior once, and I've only ever seen it in toy examples. Though I've never seen this in simulated inference. I've never seen this in anything other than contrived examples. This example was not contrived. This actually came out of Chris and I's earlier paper. We are applying the RBSL stuff in the MA2. We couldn't get BSL to work because of this multimodality, so we brought it down to MA1. It worked. This result, Chen calls it fractional normality, which I think is a pretty good description of this type of behavior. So this immediately begs the question, what happens if there's a single mode? Well, what you can actually show is under some slightly stronger assumptions, the convergence of the BSL posterior is in fact to a normal, in the sense that the total variation distance between a normal kernel, normal density, excuse me, and the BSL posterior converges at a rate of 1 m as m goes to infinity. However, moreover, the point estimators that you obtain from this density are actually also asymptotically Gaussian. However, the coverages you get from this posterior are not asymptotically valid in the frequentist sense, as is true of every Bayesian method I've ever seen that doesn't specifically account for misspecification. Right, so let's compare this behavior of BSL of what we know in the case of ABC. Right, so in the case of ABC, what we showed in a paper last year with Christian and Judith is that the ABC posterior converges in probability to a Dirac mass based on the minimizer of this distance, whatever your distance function is in ABC. Now, it's the limit of this, excuse me, I'm being sloppy here. In the BSL case, it's similar in a sense that you converge onto the limit of the minimizer of the BSL criterion, but again, there's no reason to suspect that this is a unique point. Moreover, there's no reason to suspect that these two limit problems here should give me the same value. Now, in the context of ABC, what we also showed is that if the model is misspecified, the posterior itself is not asymptotically Gaussian. It looks kind of like a deformed Gaussian in a sense, where you're renormalizing the Gaussian depending on the level of misspecification in some sense. Well, that's also true of BSL. It's not asymptotically Gaussian in general, so there's a similarity there, right, in general settings. However, as we've shown, if there's a single mode, actually, then BSL is asymptotically Gaussian. So there's similarities with ABC when the model's wrong, but if you have a single mode in BSL, you get nice Gaussian convergence, nice Gaussian concentration, whereas you don't in ABC. So that's just a nice way of saying that the limiting shape between these two methods is very, very different. And this is very strange, I find, because when the model is correct, what you can show is under some assumptions in the limit, the ABC and BSL posteriors based on the same summaries have the same asymptotic behavior. I mean, they both satisfy BVM, they both have the same variance under a correct or under an optimal choice for BSL. And again, just to note here that when the model is misspecified, I don't care which method you're using, do not believe the credible sets that come out of it. Right, so in my mind, that's a pretty severe problem in the sense that you don't know what you're converging to. You could be bimodal, you could converge onto a boundary, you just dogs and cats, right? So how do you fix this? Well, this is actually what this question, how do you fix this, is actually what started this whole research agenda. Chris and I were looking at how you deal with misspecification in BSL, and we thought, well, you can kind of adjust the summaries in some way to make sure that this incompatibility doesn't affect you. And so there's a couple of ways to do this we've figured out. So the main realization here is that when the model is misspecified, basically the simulated summaries can't replicate the behavior of the observed, in the sense that there's no value of theta such that in the limit, the observed summaries are in the support of the simulated summaries. Basically, we gave two fixes for this. I'm only going to talk about one. The fix, though, is kind of intuitively the same either way. You're going to fix this by ensuring that regardless of kind of what's happening, the simulated summaries can recover the observed summaries. So my favorite way we did this is through what we call the variance adjustment, which is by taking the standard variance covariance matrix used in BSL and adding to it kind of a perturbation that depends on these adjustment parameters. And this, there should be a 1/2 here, excuse me. This is, no, that's right, excuse me. This is done just to make sure that these adjustments are unit variance. So they have unit scale, excuse me. Then all you have to do is effectively use this matrix here, this Vn psi, where psi is the conjunction of the theta and these adjustment parameters, in place of this matrix in BSL, and just do joint inference on theta and the adjustment parameters. Now, just to show you real fast, this works really well. Let's return to the MA1 example. And remember, the problem here is that in exact BSL, what happens is you get this kind of crazy multimodality or convergence on the boundary, depending on the level of misspecification. So again, same exact model. I'm going to look at those same exact 6 levels of misspecification. And what you see is that our BSL-V fixes all of it. And what you can show is that really there is no difference here, basically up to simulation error, between the posteriors obtained when you have a small sample size, n equal 100, and a larger sample size, n equal 1,000. I.e., if you're worried about misspecification and you're running BSL, you should probably start with this, just to see what's going to happen. It's quick, it's not too bad. At least that's my opinion. Chris and Leah and everyone else may have other opinions. I think it's pretty clever though. Okay, so I'm going to go ahead and conclude. Basically, as I normally say in lots of my research, it's pretty reasonable to assume, in my opinion, that we're working with misspecified models. And as several people have said in this workshop, this creates issues for BSL. More particularly, we didn't know until now what exactly those issues were. We now know specifically those issues are that the BSL posterior can have a non-Gaussian limiting shape. It can be multimodal, or it could be kind of Gaussian, depending on where the modes are. What we also have shown is that this non-Gaussianity can really be corrected by using the adjustments we've proposed in other papers. What I also didn't mention, but I find kind of nice, is that if you're using RBSL, you can detect which features of the model you actually can't match with the assumed model. I.e., these adjustment terms, they basically turn on and turn off depending on which summaries you can't match, which is quite nice, I think. So it's an indicator of where you're wrong in a sense. So there's still some future work to do here. We're probably going to tackle in another paper. I don't have a rigorous theory of RBSL when the model is misspecified. What you can show is that when the model is correctly specified, the RBSL posterior basically behaves exactly the same as the exact BSL posterior. The adjustments don't create any inflated variance in the limit or anything like that. They still concentrate on the same points when the model is correct. When the model is not correct, I don't know. What I'd really like to figure out, though, is does this adjustment really fix the coverage issues that can happen with these credible sets in BSL when the model's wrong? My guess, though, is likely no. My hope is what you can show is that you're overly conservative, i.e., you're going to have above the kind of nominal level of coverage, because even that's kind of okay. You may not get exact coverage, but you're never going to get under coverage. That's my feeling of what is likely to happen, because you're kind of injecting more randomness into the BSL posterior this way. So my hope is that that leads to an over coverage problem and not an under coverage problem, and you can prove it. I don't know if that's the case, but that's where we're likely to look in the future. That's all I have. Thanks, guys.
Thanks so much. Thanks for an excellent presentation as per always. Okay, questions from the screen. Oh, Christian's got his mask on. Where are you? Okay. He's a masked man. You're muted. Okay. Okay. Questions?
Yeah. So, can you hear me?
Of course, yes.
We can.
Oh, you can't hear us?
Oh, can you hear us now? We can hear you. We can hear you.
Ah, ok. Je sais pas que j'ai pris le mien aussi, je pense. Yeah, so sorry, I had a question on the. Wait,
We can hear you, Christian.
sorry, this is early morning. No, so I'm not sure I followed your point that you need to have eta of y not covered by eta of z to say something, because that's very strong or very demanding that you figure out the statistics that diverges so much from the others that
it's the
it
same.
cannot be even realized from the misspecified model.
I'm being a bit cheap here in the sense that that's the way I'm using it. But I'm thinking about it, and it's probably like converging to one. So really, it's exactly the same as the incompatibility condition we have in our ABC paper, and also you have in the paper with Judith and Jean-Michel. It's the same exact condition. I'm just saying it slightly differently, in the sense that in the limit, right, I can't recover the limit or the mean, if you will, of the observed summary. So it's exactly the same condition. I'm just talking about it slightly differently.
Okay.
So that's my confusion. Does that answer your question, Christian?
Yeah. So yeah, I mean, when you think of it in the limits, it totally makes sense.
Yeah, it's in the limit. I should have been more clear about that, but it's only in the limit that this issue occurs.
Yeah, sorry about the mask, but you are sharing a room, so.
It's okay.
That's okay. Well, it's a sign of the times. It's great. And okay, so Jan has his hand up.
Yes, thanks.
Yes.
You can hear me? Yes. Thanks for the talk. That was great. I have two questions.
Yep.
First one, regarding the condition. So in practice, are there any ways to check for model misspecification? Because it might be quite expensive to simulate until I've reached the limit of simulations, right? And the second one is regarding the extended, like the variance adjusted model. How are there ways to make sure that these additional variables don't eat up like the explanatory power of the model itself?
Yeah, I mean, so let me answer your first question first. You don't actually have. There's a couple of different ways to diagnose this. I've just given you one with RVSL and RVSL-M. Those diagnose it as part of kind of a model building exercise. So you can look at that as I want to run this first. And if none of those adjustment terms turn on, that if they resemble prior effectively, that basically means you can match all the summaries. It's not a limit thing, it just means you can match them for your given data set, right? In BSL, the observed data is a vector of summaries. So what that literally means, if none of those adjustment terms turn on, is that you can match all the summaries under the model. So you can just run this and figure out, oh, is it misspecified? There is no way of just running BSL by itself and figuring out if the summaries are wrong, other than trying to do some posterior predictive check at the end of it. And in that context, it might just be easier to run this. So to answer your second question, to make sure they don't eat into the explanatory power of the model, I mean, that's a really good point. This is in a sense saying if those things turn on, it basically means your model cannot explain the data anyway. So if those variance adjustments turn on, or if the mean adjustments turn on, it means that your model cannot explain the data, or in the sense that it cannot explain the summaries. So I would make an argument there that if those turn on, your model does not have explanatory power as it is. Does that answer your question, Jan?
Yeah, thanks.
Now, Dennis and Julian both had their hands up. So we've got quickies. We're kind of up, we've got, if they're quick questions.
So my question was actually answered by the previous question. So
good, that's
thank you for that.
Julian? No?
No, actually, I did not have a question, or maybe Julien, but not.
No. Oh, sorry. Yes, it's the other one. It's
okay.
Julien.
Julian, you have a question?
Julian, you had your hand up. No, he's disappeared. I had a question, but I'm going to save it till later because we're going out to dinner, so we can, we're really, getting there.
Thanks for the questions, everybody.
So,
I'm going to go
that was
ahead and
great.
mute us.
Thank you very much. Let's give him another